So, good afternoon or morning or evening, whenever you decide to watch this. Today, we're going to be diving into the world of unit testing in the software development field or software engineering. This is a critical aspect of our work and is often defined in various ways, leading to some confusion in the pivotal experience. In my experience personally, unit testing tools have played just such a pivotal role, especially in the methodologies like XP and TDD, which is you have extreme programming and test-driven development. So now we can kind of explore the life cycles with further explanations of what some things are. So understanding the unit in software development. So now what exactly constitutes a unit in unit testing? And it's kind of an ongoing debate, and the definition can really vary based on whether you're adopting an object-oriented or procedural or functional approach. This simple kind of understanding of things, you know, has is very often like situational. It's shaped by the dynamics of the development team. So what I'll do is I'll be able, throughout the presentation, I'll share some insights of these debates and shed light on how the notation of a unit evolves within different programming, fields and things like that. So along with that, we can now move on to the sociable versus solitary dilemma. Now that we're moving on to that, there's a very distinct difference between these two approaches. So the sociable tests allow interactions with real collaborators, while solitary tests isolate the unit under the test. And I'll kind of be able to discuss the historical perspectives, which is the shift from sociable to solitary testing, and also further down the slide, the emergence of the mock objects and the tools presented in this context. So striking the right balance here. So this is a nice little speed in unit testing and things like that. Speed is the essence of the unit testing. When we're talking about tests within a small scope that we write as programmers and execute very rapidly. So I'll introduce you to a few concepts over the next few slides, the compile suite and the commit suite. And I'll definitely emphasize the importance of frequent testing for just early bug detections. But speedy tests contribute significantly to just the agility and efficiency of the developing process. So now, as we continue into our explorations into the development of software testing, we can now shift to the focus of the concept of a regular test in software development. These tests here play a pivotal role in ensuring the reliability and functionability of our software. To kind of explain this further and illustrate how this works, we can dive into a simple Java example that is involving an object-oriented warehouse object, showcasing just typical testing scenarios and things like that. Now, from there, we have the ability to move on to XUnit testing principles. So the way this is XUnit testing principles with JUnit as as we look at things, a widely used testing framework in Java. So there are four phases. There's a four-phase sequence that goes along with using the JUnit. It is setup, exercise, verify, and tear down. And we're kind of highlighting the essentialness aspects of each phase. Using these kind of examples throughout the slide, we'll be able to demonstrate and emphasizing importance on these, reliable tests that we have the ability to create and develop. Now, understanding the system or system under test SUT or collaborators, the SUT or system under test represents the primary object we're going to be focused on testing, like an order object. Just to clarify the distinction between SUT and collaborators, introducing the terms such as object under testing or system under testings, while collaborators, on the other hand, are objects necessary for the system under testing to function properly. Now, state verification and X testing. State verification is just a crucial aspect of regular test. It involves determining if the exercise method worked correctly by examining the state of the system under testing and its collaborators. I will illustrate. I do apologize for my dog. My neighbor has just come home and he decided he wanted to say hello. So I'm going to start from the beginning of this slide. So state verification is a critical aspect of its regular tests. It involves determining if the exercise method worked correctly by examining the state of the system under test and its collaborators. A practical code snippet, I believe I have included further on into the presentation, but we will, get to that when we get there. Now, just a simple conclusion on the regular tests. As we wrap up our discussion on the regular tests, we can recap the principles of the simplicity and the clarity and the state verification for reliable and efficient testing. It's important to note that garbage collection implicity handles the teardown section of the regular test principle, which is contributing very highly to their simplicity. So just in a very simple thing, in conclusion, regular tests play a crucial role in ensuring software reliability and maintaining functionality. Now we can move on to the difference between mocks and stubs. Understanding that tests double in software. So the difference between, I'm sorry, I'm getting just a little turned around here. So the definition of test doubles are pretend objects used for testing in real objects. The origin comes from the term from the idea of a stunt double in a movie. And the purpose is to kind of isolate the specific elements of the software testing itself. So now continuing to kind of move further on, especially with the double testing categories, we can now look into Gerard Mazzaro's vocabulary, which just categorizing text double into 5 specific kinds, and I'll further explain each category. So the 5 categories that we do have are dummy, fake, stubs, spies, and mocks. Dummy objects passed around, but not used in a test specifically. Fake objects have working implementations, but are not suitable for production. Stubs provide canned answers during the tests. Spies record information based on calls like email, service tracking, text messages, things that are sent. And mocks are pre-programmed with expectations emphasizing the behavior verification. So understanding that these distinctions is crucial for choosing the right test double to using different testing scenarios. Now we can move on and further explain mocks versus stubs in the testing. So we can zoom into the distinction between mocks and stubs in testing. I'll explain the difference between state verification and behavior verification. We will also, show some, discuss some examples, including the mail service stub for testing email sending behavior with the state verification and the mock for the same scenario, emphasizing the aspect of, behaviors during testing. Applications of double tests in scenarios. So the practical use of test doubles come into play when real objects are awkward and kind of unsuitable for testing. So the extended example here is, sending the email if an order fails to be filled. So that's kind of an application of it. A stub example is a mail service stub with a state message verification for counting sent messages. And then the mock example is like using mock's behavior verification for testing the order's interaction with the mailer. So now we're going to kind of just recap. So in conclusion, for those test doubles prove invaluable in isolating the test-specific software components, emphasizing the flexibility offered by stubs, which can use either state or behavior verification, while mocks rely on behavior solely. I'll leave you with some of the best practices in choosing an appropriate type based on, the testing needs. Additionally, we can explore the testing spry and hybrid between mocks and subs. But for now, what we're going to do is we're going to move on to the next part, which is classical and Moxis test-driven development, TDD, which is TDD is, kind of a very important factor when it comes to software engineering. So now that we can shift our focus into the methodologies of test-driven development, we will explore the difference between the classical and Moxis TDD. While classical TDD test-driven development emphasizes using real objects whenever possible, resorting to doubles only when necessary. In contrast, though, Moxis TDD always uses mocks for an objects with interesting behavior. I will work on providing just some insight of the origins of these approach known as Detroit style and/or London style for Moxix based on their XP origins. So now we have to work on choosing in between state and behavior verification. So we can take a very easy dive into this, but it's more of a deeper dive into the decision-making process of TDD. The choice between state and behavior verification depends on a whole ton of factors. So we can discuss the matters, and easy collaborations might not necessitate mocks. Classic TDD tends to use the real objects and state verification, while Moxis TDD leans towards behavior verification. Except there are some exceptions, such as cases where testing catch might be warranted behavior verification, even in the classical TDD. So now driving TDD, we're going to still talk about the classic first Moxix style. We can explore the test-driven development is driven differently in classic than in Moxis styles. Classic TDD emphasizes the middle-out approach and domain-first development, while on the other hand, Moxis TDD advocates for need-driven development, working outside in. Where classical TDD objects might require more of a fixture setup with object mothers, while Moxis TDD emphasizes, or enthusiasts, might argue that Moxis reduces the fixture setup complexity. Test isolation in classic and mock TDD. This is an essential aspect of the TDD is test isolation. An impact of bugs in different and classical Moxis TDD. In Moxis TDD, bugs usually impact only tests related to the buggy object, while the classic TDD, bugs can cause the ripple effect across the tests using that object itself. Discussing how coarse-grained tests in classical TDD may complicate bug identification, with classics arguing it's manageable, while the Moxists emphasize the clarity of the Moxis test. So then we have a mock toolkit. So some mock toolkits specify detailed expectation impacting factors. Coupling to implementations and refactoring. We could discuss the critical aspect of the coupling test to implementation and the challenges it poses during refactoring. Moxis tests are more coupled to implementation and may break the method changes, impacting the refactoring process. We can touch up on the challenges posed by some of the mock toolkits that specifically detail the impacting of the refactoring process. So bug impact, bugs usually can only impact tests related to the self-buddy object, while classic TDD bugs are the ripple effect. We've discussed this in the last slide. Classics argue it's manageable, while Moxis more emphasize the clarity of the Moxis traits. Principles of a good test. Software testing is the heart of ensuring quality and reliable software products. So a TRIP principle has provided a comprehensive framework for creating a high quality test. It highlights the essential qualities and defining what a high quality test is. So a TRIP itself stands for automatic, thorough, repeatable, and independent, and professional. Remembering these principles are the foundation of effective testing, ensuring that our tests contribute meaningfully to the development process. Now, we can focus on the core principles of things. So the test should be automatic, meaning that the process of invoking tests and checking results should be automatic and limiting manual intervention. They should be also thorough, covering key paths and scenario to ensure the comprehensive test coverage. Additionally, tests must be repeatable and independent, yielding constant results each time and not relying on other tests. These principles here form the backbone of what our definition of a reliable test is. We can now move forward and move on to the best practices. Tests should not only be automatic, but also professional, characterized by a well-designed test code. Emphasizing the need for speed, we stress the importance of a fast tests. Tests should also, though, be readable, ensuring that anyone can understand them easily. Additional guidelines, including considerations of ownership, and allowing low benefit work, avoiding low benefit work. In conclusion, we can recap a TRIP principles and underscore the pivotal role of a good test in the efficient, reliable development. So the definition, effective unit tests are fundamental to ensuring the functionality, reliability, maintainability of the software components. While the importance, they serve the first line of defense against bugs that contribute completely over the overall health of the code base. So there are some characteristics to the basic unit test. So we can explore these characteristics. They should be environmentally independent, isolated from other tests, not rely on external data, and should have no side effects. Adhering to these requirements ensures the test is portable, independent, crucial aspects for a robust testing strategy. Characteristics of a good and a better unit test. Characteristics of a good and better unit test. Elevating our understanding, we progress to the characteristics of the good and better testing. Good unit tests not only adhere to the basics, but also assert results. Test a single unit of work, covers all paths of the code. Better unit testing will then move a step further by testing and asserting edge cases, running fast, which are ideally under 100 milliseconds, and being well factored, treated as an essential code. We can conclude by emphasizing the progression from basic to better unit testing, encouraging the commitment to the continuous improvement over our testing practices. Importance of test discipline. It's not uncommon for developers to overlook crucial elements of the unit test, resulting in an unclear and unhelpful test suites. Picture a scenario where confusion reigns within a test suite. Our visual representation aims to capture the state of uncertainty that arises without the proper test discipline. Your first line of defense. So now we can look at the evidence of test-driven development. TDD reduces bug density and code complexity. It encourages modular design, enhancing agility, and empirical evidence supports that TDD's effectiveness. So the anatomy of a good unit test. Writing tests first is very crucial. Clear test failure reports are akin to bug reports. Unit testing does serve multiple purposes in design aid documentation, QA, and continuous delivery. So now we can kind of look at the compose example that creating a good unit test compose example. Well, we'll walk through the specific steps to dividing the behavior requirement, utilizing the equal assertion for clarity, and answering the fundamental questions about actual and expected output. Automated test and continuous delivery. Shifting gears now, we can now discuss the automated test and continuous delivery. Here we can provide an overview of how automated tests are integral in a continuous delivery system. A visual representation. The cost of neglecting these test suites. This is kind of rather important. So quality tests enhance developers' productivity. In the impact of neglecting these tests, we can discuss how quality tests enhance developer productivity, the significant cost of bugs reaching product production, and positive return on investment or ROI associated with TDD. Types of tests in detail. So unit and integration. We can provide the breakdown unit tests for individual components, lightning fast and serving as good bug reports, while integration tests ensure proper collaboration between the components. So integration tests for collaboration between components and ensuring proper interactions. The functionality tests ensuring application behavior from the user perspective. Role for the further functional test and smoke testing after development. Importance of continuous delivery for faster and safer releases. Next, we can dive into the introduction of software testing. So software testing is a crucial process of validating and verifying software artifacts and behaviors. The object here is to provide an objective, independent view, allowing us to assess and understand the risks associated with software implementation. Key areas that we can talk about include examining the completeness and the correctness of the product requirements, reviewing the product architecture, and designing and collaborating with developers for coding improvements. The purpose and limitations. The primary purpose is to provide objective, independent information about software quality and the risk of failure. However, it is essential to acknowledge the limitations. Testing cannot identify all failures, guarantees proper functioning under all conditions, or replaces the need for early detection and crucial and correction of failures. Faults and failures. In understanding the faults and failures, we have to explore the software faults leading to these failures. We can gain insight on how the requirement gaps and causes defects and the challenges in testing all combination of inputs and preconditions. Combination, a combinatorial test becomes crucial for effective testing. Economic impact and roles. In software testing, we examine the significant impacts of software bugs on the economy. We can also delve into the common practices such as outsourcing testing for cost effectiveness and work on getting an understanding of the roles in software testing from the test managers to analysts is crucial, along with the evolution of testing history and the separation of debugging and testing. Now we can move on to a little bit more of a interesting topic, gray box testing. So the definition of gray box testing involves the knowledge of internal instructions and algorithm while executing tests at a user or a black box level. We can discuss the importance of both source code and executable binary and the potential inclusion of reverse engineering for boundary values or such the error message. Levels of software testing. These include unit testing, integration testing, system testing, and acceptance testing. Each level, though, has a very specific focus and purpose with the person who's using it with the user exceptions test or UAT, taking the center stage for operational readiness. So for unit and integration testing, we can dive into the specifics for each. Unit testing focuses on verifying specific sections of code, usually at the function or class level, while integration testing verifies interfaces between components, ensuring they work seamlessly together. And this is just a very fundamental, this unit and integration testing is a fundamental to building a robust software or one that is used very well, something that is working together properly. So we can now transition into the acceptance testing. While we explore user acceptance test or UAT or operational acceptance test or OAT, contractually and regulatory acceptance testing, each type plays a unique role in ensuring that software meets the expectations of the person who needs it. We can emphasize placed on the hands-off process of this. So unit testing focuses on verifying specific codes, integration, verification, and importance of ensuring components work seamlessly together. Functional and non-functional testing. Functional testing in itself involves verifying very specific actions or functions of the program that is written, while the non-functional testing addresses the aspect not related to specific functions, such as scalability or security. We can also talk about continuous testing or destructive testing, showcasing the conditions in each testing landscape. But as we continue to move through the next couple slides, keep in mind that effective software testing is not just about finding bugs. It's about ensuring the reliability, functionality, and quality of the software we develop. Now we can move on to the critical domain of development testing in software development. Development testing is not just a phrase, it is a crucial process focused on both defect prevention and detection. The primary goal is to eliminate construction errors before advancing to other testing phases. Various strategies that we could use to contribute this includes static code analysis, data flow analysis, metric analysis, peer code reviews, unit testing, code cover analysis, and traceability. These practices collectively form a very good foundation for building a high quality software program right from the early stages of development. Moving forward, we explore now of A/B testing. This is a controlled experiment is designed to compare the effectiveness and proposed change with the current approach. The process involved routing users to either a current version, which is going to be the controlled, or a modified version, which is the treatment, And the data collection of that will determine which version performs better at achieving the desired outcome, A or B testing, as you can kind of see by the name. It's a very powerful methodology for making informed decisions about changes, enhancements, or optimizations in the software, ensuring that improvements are data-driven and impactful. We can move to the slide assessing concurrent computing with concurrent testing. We have now entered this world of evaluating the behavior and performance of software and system under normal usage conditions. Concurrent testing is the instrumental in exposing issues like deadlocks, race conditions, and problems with the shared memory or resource handling. Its importance lies on ensuring peak performance, especially in environments with concurrent processing, which is increasingly common in the new modern software architectures. We can explore the sophisticated property of the testing technique. This method focuses on asserting the truth of the properties that should hold every pair of input and output. For instance, it involves verifying that every output from a serialization function is accepted by the corresponding deserialization function. Property testing is also known as quick check testing and is popularized by the Haskell library quick check. This approach ensures that our software not only produces correct results, but also adheres for specific properties across various inputs and outputs. Now, our journey really does kind of conclude with the VCR testing. On this slide for VCR testing for regression, also known as record and replay testing. This technique specifically enhances the reliability and speed of regression, especially when dealing with slow or irreliable external components. These processes involve recording interactions with the external components and replaying them in a subsequent test run. VCR testing is particularly useful when testing third-party APIs that may be outside of the tester or the user's control, ensuring that the software interacts seamlessly with the external systems. We can explore these diverse testing methodologies. Remember that each of them play a crucial role in different aspects of the software development lifecycle, from preventing construction errors to comparing different versions in controlled experiments and ensuring peak performance in concurrent environments. These testing techniques contribute to the overall quality, reliability, and success of our software projects. And now we'll move on to unit testing and software development. So now we can shift our focus to the cornerstone of software quality, unit testing. Unit testing in practice of rigorously testing individual units or components of the software to ensure they function as independents, as intended. Its roots trace back to the prevalence of unit testing frameworks that gained momentum with the development of JUnit by Kent Beck and Eric Gamma in 1997. This was a pivotal moment occurred when Google embraced the automated testing around 2005, 2006, making it just a significant industry shift towards a more robust testing strategy and practice. So the definition of a unit is the smallest isolatable component in an application, such as a function, subroutine, method, or property. Types of procedural programming, a unit could be an entire module or more commonly an individual function of that procedure. And there are some types in the object-oriented program. A unit is often an entire interface, example, a class, or an individual method. So some of the advantages of unit testing, you know, that it brings to the table is early problem detection is a key advantage in identifying issues in the development cycle, including bugs and specification flaws. This early detection translates to a cost reduction, which everybody likes, as finding and fixing bugs before the coding completion is more cost effective. Now, TDD, where tests are written before code, ensure that code completeness and quick bug IDing, ultimately allowing for more frequent release and faster iteration cycles. Enables a faster iteration cycles by addressing issues at the component level. So demonstrating a unit case for the adder interface applications. Unit testing is crucial in being XP, enabling test-driven development and emergent design, and Frameworks overview of the unit testing frameworks, both languages and supported by third party. Challenges. Wow, sorry, that rain is coming down hard out there. Incomplete error coverage. Unit testing cannot evaluate every execution path and is non-trivial programs. Integration and sub-level errors. They don't catch integration errors on broader system errors. The combinational, really having a hard time pronouncing that word, problem requires multiple tests for every line of code, which increases the effort and time it takes to actually get these codes to run. Difficult in realistic tests, setting up a realistic test and useful can be challenging due to the fact that you need to be able to have a realistic scenario. So now we can move on to the introduction of the mock objects. So mock objects are simulated the behavior of real objects in a controlled way. To crash test dummies used by car designers, this simulation is primarily employed in software testing to ensure that complex and real objects are practically testable. So definition, mock objects simulate the behavior of real objects in a controlled way. Analogy, similar to the crash test dummies in the car. An application, they're widely used in generic programming and object-oriented programming. Now, why do we use mock objects? In the realm of unit testing, mock objects play a pivotal role when dealing with non-deterministic results or difficult to reproduce states, slow processes, and non-existing objects or objects with testing specific information. They are especially valuable when a real object is impractical or impossible for unit testing. Now we can kind of, peek under the hood of the implementation. So when we peek under the hood, we have to have an understanding of the technical detail of mock objects. These objects mimic the interactions with real, allowing seamless integration into client code. The frameworks enable the specification of method invocations, order parameters, and return values. They can simulate the behavior of even complex objects, facilitating testing under different states. Now, there are some classifications here. So some of the classifications, mocks, fakes, stubs, understanding the classifications in mocking is essential. So the terms that I just stated, mocks, fakes, and stubs, are terms that are vary across literature, but essentially represent production objects in a testing environment. They span the simplicity spectrum, ranging from simple and prearranged responses, which are stubs, to complex logic-rich simulations, which are mocks. And mocks may include assertions about other methods, order, data, consistency across the calls. But there is some, as we conclude this exploration, let's first recognize that any tool, mock objects come with their own set of challenges and limitations. There can be concerns about the coupling where mock objects may tightly couple unit tests to coding it to code implementation, risk test failure during the refactoring, but overusing mock objects may increase test maintenance during this whole system evaluation and its accuracy in the modeling their behavior, though. So unit testing and the use of mock objects are powerful tools in the arsenal, ensuring that we produce a high quality software. They contribute significantly to the reliability, maintainability, and efficiency of our code. As well, we can navigate through the complexities of software testing. These practices stand as pillars to supporting the creation of a robust, resilient software system. So, coupling concerns can be tightly coupled with unit test to code implementation, maintenance overhead overusing, may increase test maintenance during system evaluation, and accuracy challenges. Accuracy challenges in modeling the behavior of mocked objects is crucial, and accuracies can lead to passing tests but runtime failures. And that there is going to be the end of my presentation on unit testing. This is Christopher Pavsicki from Du Young Park's software engineering course.